Measures of dependence. For a little bit of notational brevity, we're going to denote e of x by mu sub x and e of y by mu sub y. And this also reminds you that they're constants, they're not random variables. What I want to do is define covariance. The difference between the expected value of the product and the product of the expected values is, in fact, the covariance between two random variables, x and y. Now, this theorem indicates that there are two different ways of computing that. We can use the difference directly, or we can first subtract off the mean, or the expected value, from each of the two random variables, x and y, compute the product, and then take the expected value. Proving that these are equivalent is quite easy. In fact, if I take the right-hand side, the expected value of x minus mu x times y minus mu y, and I expand it, I get four terms. X times y minus mu xy minus mu yx plus mu x mu y. But because, for example, mu x is a constant, when I compute the expected value of mu x times y, I can remove the constant outside. I'm left with mu x times e of y, or mu x times mu y. In other words, the last three terms in this sum, the expected value of mu xy, the expected value of mu yx, and mu x mu y, are all the same. Turns out we're subtracting off that product, mu x mu y, twice, adding it in once, and we end up with e of xy minus mu x mu y. So I could choose either of these two definitions, these two equivalent quantities, to define covariance. It's usually defined to be the second. The covariance between x and y, denoted COV x of y, is the expected value of x minus mu x times y minus mu of y, the expected value of that product. The covariance is a measure of association between two random variables, a measure of a certain kind of dependence, a measure of whether x and y tend to move in similar directions simultaneously, or in opposite directions, or have no such tendency at all. Covariance continued. In this figure you see four panels, and each one of those refers to a certain uniform distribution. For example, I have about 100 points appearing, and in panel A, I'm assuming that my distribution is uniform on each of those 100 points, that the value of x will be taken, if you choose a point at random, the value of x will be taken as the x-coordinate of the point, the value of y as the y-coordinate. I've also drawn a vertical line at the value of mu x, and a horizontal line at the value of mu sub y. And this, of course, chops the graph into four different quadrants. The upper right quadrant and the lower left quadrant I've labeled with a plus sign. Those on the upper left and lower right with a minus sign. This is simply to remind you of the value of the sign of the product, x minus mu of x times y minus mu of y. This is a product which is positive in the upper right because both values are positive, and positive in the lower left because both values there are negative. Whereas in the other two quadrants, the sign of that product is negative. Of course, the vast majority of the points appear to correspond to positive values of that product. Only a small number are in the negative quadrant. Moreover, if you look at the magnitude of the product, x minus mu of x times y minus mu of y, the magnitude appears to be much greater in panel A, in the positive quadrants, than in the negative. And all this is to say that the expected value of the product, x minus mu of x times y minus mu of y, will tend to be positive, and much larger in a figure like panel A than it would be in, for example, panel B. In panel B, we see similar behavior, but there's a little more balance between the positive and negative values. The expected value of the product, x minus mu of x times y minus mu of y, the covariance is still positive, but probably significantly smaller than it was in panel A. In panel C, we see approximately the same number of points in each of the quadrants and similar magnitudes, and so in this case, the expected value of the product, the covariance, is very likely close to zero. In panel D, finally, the negative quadrants predominate. The covariance should be negative, and very negative, in absolute value similar to the magnitude in panel A. So in summary, in those four figures, the covariance was positive in panel A and large, positive in panel B but smaller, approximately zero in panel C, and very negative in panel D. A large positive covariance seemed to indicate a fairly strong positive linear relationship between random variables x and y. There is a tendency here for large x to be associated with large y, and small x with small y. On the other hand, a negative covariance, especially a very negative covariance, indicates also a strong linear relationship, but a negative one with negative slope between x and y. That indicates that very large values of x would correspond to small values of y, and vice versa. A covariance near zero seems to imply little or no linear relationship at all between the two. Example: covariance. Below we see a very simple probability function. The random variables x and y have 4 possible values, each with probability 1/4. The possible pairs of values are depicted in this graph. They're 0, -1, 0, +1, 1, 0, and -1, 0. And the probability function is listed as well. It's pretty clear from the graph that there's no linear relationship between x and y. Indeed, if we compute the expected value of x, it's 0, the expected value of y, it's 0, and the expected value of x times y, also 0, equal to e of x times e of y. So the covariance in this case is 0. But are the two random variables independent of one another? To answer that question, you have to ask yourself whether, if you were given the value of y, you would change the distribution assigned to the random variable x. Certainly looks like it. It looks like if y is equal to -1, if I'm told y is equal to -1, for example, I know that x must be 0 in this case. If I'm told that y is equal to 0, I know x must be either -1 or +1. To confirm that x and y are dependent, all we need to do is find some pair of values like -1, -1, and compare the joint probability function with the product f of x minus 1 times f of y minus 1. Indeed, the joint is not equal to the product in this case. The former is 0, the latter is 1/4 times 1/4, so they're dependent. In summary, it's possible for dependent random variables to have a covariance of 0. A covariance of 0 doesn't prove that they're independent. What it indicates is there is no linear dependence between x and y. Of course, that's the most common kind of dependence we're likely to find in practice. You've seen laws for dealing with expected value and variance. Here are some corresponding laws for dealing with covariance. The first says that the covariance of a random variable with itself is its variance. The second says the covariance of x with y is identical to the covariance of y with x. The third is the linearity property of covariance. If I have two constants, a and b, the covariance of the random variable ax plus b with y is a times the covariance of x and y. Notice that b is not involved at all. In order to prove these assertions, we'll denote e of x by mu sub x and e of y by mu sub y. By definition, the covariance of x with x is the expected value of x minus mu of x times x minus mu of x, which, of course, is just x minus mu of x squared. The expected value of x minus mu x squared is the definition of variance. That proves 1. The covariance of x with y is, by definition, the expected value of x minus mu of x times y minus mu of y, which, of course, is identical to the expected value of y minus mu of y times x minus mu of x, since we can interchange any two terms in product, and that is, indeed, the definition of the covariance of y minus x. So this property, too, follows essentially by the definition of covariance. The third property is that of linearity, the covariance of ax plus b with y. And the first thing you should note is that when you take ax plus b and subtract off its own expected value, b vanishes, and we're left with ax minus a mu of x. So the expected value of the product of ax plus b minus its own expectation times y minus mu of y is the expected value of ax minus a mu of x times y minus mu of y. And that constant a factors outside the expected value, so we're left with a times the covariance of x, y. There's an easy device for remembering some of the rules for combining variances and covariances. Covariance is an inner product. It behaves exactly like a product does, where a product of something with itself gives us a square. Covariance of something with itself is the variance, and so the variance is analogous to a square, the covariance to a product. Let's use this, for example, to establish a rule for determining the variance of a linear combination. For example, the variance of ax plus by, where a and b are constants. Suppose I take the corresponding quantity ax plus by algebraically and square it. We get, of course, three terms: a squared x squared plus b squared y squared plus 2ab times xy. Remember that ax plus by squared is analogous to the variance of ax plus by in the world of random variables. Similarly, a squared x squared is analogous to a squared times the variance of x. B squared y squared to b squared times the variance of y. And 2ab xy to 2ab covariance between x and y. So the rule that you see on the bottom of this slide is a rule for establishing the variance of a linear combination. It's easy to prove this, but it's easy to remember it by analogy with simple algebraic. The first is that a covariance has an upper bound. The covariance between x and y is less than the product of the standard deviation of x times the standard deviation of y. Actually, that's a bound for the absolute value of the covariance, which means the covariance is also greater than the negative of the right-hand side, minus the product of the two standard deviations. And the fifth property is one we've already seen. If x and y are independent, then the covariance between x and y is 0. Let's first prove the property 4. Suppose I have a constant value for t. Well, by constant, I mean a non-random value for t. If you were to square the quantity x minus ty, what would you get? You'd get x squared minus 2t xy plus t squared y squared. And analogously, in the world of random variables, this tells us that the variance of x minus ty is equal to the variance of x minus 2t times the covariance between x and y plus t squared times the variance of y. That quantity, because it's a variance, is always greater than or equal to 0. This means we have a quadratic equation. A quadratic function of t is always greater than or equal to 0. When is this true? It's true when the quadratic equation, when we set it equal to 0, we have either no real roots or one real root. If you had two real roots, it would have to dip below 0 at some point. We can all remember how to determine whether a quadratic equation has at most one real root. This means that the discriminant, what we referred to in high school probably as b squared minus 4ac, the discriminant must be less than or equal to 0. In this case, that tells us that 2 times the covariance between x and y squared minus 4 times the variance of y times the variance of x is less than or equal to 0. And if we move the variances to the right-hand side of that inequality, divide through by 4, and take the square root, we end up discovering that the absolute value of the covariance is less than the product of the two standard deviations as required. The last property, that the covariance is 0 if x and y are independent, we've already essentially seen. It says, recall that when x and y are independent, e of xy is equal to e of x times e of y. This implies that the covariance between x and y, which is e of xy minus e of x times e of y, must be equal to 0. Actually, we've also discovered that a converse to this statement is not true, that it's possible that the covariance is 0 and yet x and y be dependent. Although the covariance is a measure of dependence or association of a particular kind, linear, it changes when we change the unit of measurement. So whether I measure distances in miles or kilometers will affect the covariance. Because I don't know an upper bound for covariance in general, it's harder to know whether a covariance of 3,600 means that random variables are highly linearly related or not. We solve this problem by rescaling the covariance to get the correlation coefficient, rho sub xy. Rho sub xy is defined to be the covariance between x and y divided by the product of the two standard deviations, standard deviation of x times the standard deviation of y. Recall that the denominator is the maximum possible value for the absolute value of the covariance. So this means the correlation coefficient must fall in the interval from -1 up to +1. This makes it easier to interpret a correlation coefficient that's close to one or other of these two limits, 0.98 or, say, minus 0.98. So it's also the extent of a linear relationship between the two random variables x and y, but it has the advantage of a built-in maximum and minimum, a built-in scale, and the advantage that it doesn't depend on the unit of measurement, whether I measure x in terms of pounds or grams, y in terms of some other unit, miles or kilometers, it makes no difference to the correlation coefficient. At the bottom of this slide, you'll see two examples, one in which the correlation coefficient is close to 1, so there is a very nearly a linear perfect linear relationship between x and y with positive slope. The other example in which the correlation coefficient is close to -1, indicating that it's very close to a line with negative slope. We've already seen correlation coefficient is a quantity which lies always between -1 and +1. Indeed, if it's exactly equal to either one of those two extremes, +1 or -1, then its x and y are perfectly linearly related, which means that, for example, y is a linear function of x. If it has positive slope, rho is +1. If it has negative slope, rho is -1. Review question 1. Show that if rho of xy is the correlation coefficient between any two random variables x and y, and a and b are constants, let's suppose that a is positive, a is greater than 0, then the correlation coefficient between ax plus b and y is also rho xy. Solution. The correlation coefficient between ax plus b and y has in its numerator the covariance between ax plus b and y. Recall that that's just a times the covariance between x and y. What about the denominator? The denominator contains the square root of the variance of ax plus b. Remember that the variance of ax plus b is a squared times the variance of x, giving us the second term on the first line of this proof, a covariance xy divided by the square root of a squared variance of x times the square root of the variance of y. There's not much left except to remove that a squared outside the square root sign in the denominator. But here's where you need to be careful. When you remove a squared from a square root, it becomes the absolute value of a. Recall that the square root sign means the positive square root of a number. And so I now have in the denominator the absolute value of a times the square root of variance of x. In the numerator, I have a times the covariance of x and y. That ratio is rho xy, provided that a is positive, because then the absolute value of a is identical to a. Part B is very similar, except that here we're specifying what a is. A is, say, -2, which is now negative, and b is 3. And I want to show in this case that rho xy is -1, where y is -2x plus 3. Solution. For part B, we have very similar calculation. The covariance of -2x plus 3 with x in the numerator becomes -2 times the covariance of x with itself. The variance of -2x plus 3 in the denominator becomes 4 times the variance of x. And again, we take the square root of 4 outside. We're left in the numerator with -2 times the variance of x, and in the denominator we're left with 2 times the variance of x. That ratio is -1. Review question 2. Suppose x and y have joint probability function given in this table. Do you expect the correlation coefficient rho xy to be positive or negative? Do you think it's close to 1 or -1? Let's calculate the correlation coefficient to confirm our suspicions. Solution. There's a somewhat higher probability of x and y taking the same values, for example, -1 or +1. So that means that large values of x seem to be somewhat associated with large values of y, small values of x with small values of y. This would seem to indicate that the correlation coefficient is positive. But there doesn't look to be a very strong linear relationship between the two. The correlation is probably not very close to plus or minus 1. To calculate the correlation coefficient, first notice that both the expected value of x and the expected value of y are 0. And to get the expected value of the product, e of x times y, we need only add over the 4 cases in which neither x nor y are 0 in the table. And that's the sum of 2/6 plus 2/6, minus 1/6 minus 1/6. It gives us e of xy equals 2/6. The variance of x, the variance of y are both 1 in this case, and so the correlation coefficient is the covariance, 2/6, divided by the product of the standard deviations, 1 times 1, or 2/6.